Hello and welcome to this video. My name is Keshav Jadhav, and in this video I will explain how to solve a numerical based on psychrometry chart in which we have to calculate ventilation load, grand total heat, grand sensible heat factor, that is GSHF, then effective room sensible heat factor, that is ERSHF, and apparatus dew point temperature, that is ADP. Also, I will explain how to draw effective room sensible heat factor line, then room sensible heat factor line, and grand sensible heat factor line. So, numerical is like this. A commercial shop has following loads: room sensible heat 58.15 kilowatt, room latent heat 14.54 kilowatt. The summer outside and inside design conditions are: outside condition is 40 degrees Celsius dry bulb temperature and 27 degrees Celsius wet bulb temperature. Inside room condition is 25 degrees Celsius dry bulb temperature and 50% relative humidity. 70 meter cube per minute of ventilation air is used, which is outside air. Determine the following if bypass factor of the cooling coil is 0.15. First, ventilation load. Second, grand total heat. Third, grand sensible heat factor. Fourth, effective room sensible heat factor. And fifth, apparatus dew point. So first we will write given data. So here in numerical, room sensible heat load is given. So we can write room sensible heat is equal to 58.15 kilowatt. Then room latent heat, which is equal to 14.54 kilowatt. Then outside condition and inside room conditions are given. So outside condition it is 0.1 and inside room condition it is 0.2. So here outside condition is 40 degrees Celsius dry bulb temperature. So we can write TD1 is equal to 40 degrees Celsius, which is outside dry bulb temperature, and outside wet bulb temperature it is TW1 27 degrees Celsius, and inside room condition can be indicated with suffix 2. So 25 degrees Celsius dry bulb temperature, which is TD2, and 50% relative humidity means phi2, it is 50%. Then 70 meter cube per minute of ventilation air. Ventilation air, it is the outside air. So it is V1. So V1 is equal to 70 meter cube per minute. Then bypass factor of cooling coil is given. So BPF is equal to 0.15. And we have to calculate ventilation load, grand total heat, grand sensible heat factor, then effective room sensible heat factor, and apparatus dew point temperature. So this is the given data. So this is the example of summer air conditioning system. So we can draw layout for the summer air conditioning system. So point 1, it is the outside air where dry bulb temperature, which is TD1 is equal to 40 degrees Celsius, and wet bulb temperature TW1 is equal to 27 degrees Celsius. And inside room condition it is 0.2. So here dry bulb temperature TD2 is equal to 25 degrees Celsius and relative humidity phi2 is equal to 50%. So this outside air and this return air, which is recirculated air, it is mixed in the mixing chamber, and then this air, it is supplied over the cooling coil having bypass factor 0.15, and then it is supplied to the room. So here outside condition is 0.1, inside room condition is 0.2. After mixing it is 0.3. Then after passing that air over the cooling coil it is 0.4. So we have outside condition 0.1 and inside room condition 0.2. So we can locate these points on psychrometry chart. So this is typical psychrometry chart. So on this psychrometry chart, on x-axis it is dry bulb temperature, on y-axis it is the humidity ratio, here it is the sensible heat factor scale, this is the enthalpy values, these inclined lines are constant enthalpy line as well as constant variable temperature lines. These curved lines are relative humidity lines. So we have to look at outside condition, dry bulb temperature 40 degrees Celsius and wet bulb temperature 27 degrees Celsius. So on x-axis, here it is the 40 degrees Celsius dry bulb temperature. So we can draw vertical line from this and 27 degrees Celsius wet bulb temperature. So here it is 25, 26, 27. So from this 27, we can draw a line along constant wet bulb temperature line like this. And here, this intersection point, it is the outside air condition point 1. Similarly, we can locate inside room condition where dry bulb temperature is 25 degrees Celsius and relative humidity 50%. So here it is the 25 degrees Celsius dry bulb temperature. So draw vertical line from this, and here this curve line, it is for 50% relative humidity line. So intersection point, it is the point 2, which is inside room condition. So in this way, we can locate point 1 and point 2 on psychrometry chart. Now, to read the values of enthalpies at point 1 and point 2, we can draw a line along constant enthalpy line up to this enthalpy scale like this. So we can read the enthalpy at point 1, which is just greater than 85. So we can say it is 85.2, and from point 2 we can draw a line. So here it is about 50. So enthalpy at point 2, it is 50. So we can write enthalpy at point 1 85.20 kilojoule per kg of dry air, and enthalpy at point 2, that is inside room condition, H2 is equal to 50 kilojoule per kg of dry air. So from psychrometry chart, we have calculated values of enthalpies at point 1 and at point 2. Now we have to calculate ventilation load. So to calculate ventilation load, we have outside air total heat, which is equal to outside air sensible heat plus outside air latent heat. Also, we have outside air sensible heat is equal to EMCP delta T. Here, delta T, it is the dry bulb temperature of outside air minus dry bulb temperature of inside room air. And outside air total heat we can calculate by using formula EM into delta H. Here delta H, it is the enthalpy of outside air minus enthalpy of inside air. Now here we can put value of density of air is equal to 1.2 kg per meter cube, and specific heat is equal to 1.02 kilojoule per kg Kelvin. And if we do the unit conversion, then we will get outside air sensible heat is equal to 0.02044 into V1 into TD1 minus TD2, and outside air total heat is equal to 0.02 into V1 into H1 minus H2. Here EM, it is density of air into volume of air. Here V1, it is volume of outside air, it is in meter cube per second. But here after putting values of density of air and specific heat of air, and by doing unit conversion, so instead of taking volume of air in meter cube per second, we can take in meter cube per minute, because in most of the numericals it is given in meter cube per minute. So here by doing that unit conversion, that is by multiplying with 60, we will get these formulas. So we will be using these formulas to calculate outside air sensible heat and outside air total heat. Here V1, it is in meter cube per minute. So by using this formula, we will put the values of V1, TD1, TD2, H1 and H2. We will get outside air sensible heat is equal to 21.462 kilowatt, and outside air total heat is equal to 49.28 kilowatt. And by using this formula, we can calculate outside air latent heat. So we can read this formula as outside air latent heat is equal to outside air total heat minus outside air sensible heat. So by putting these two values, we will get outside air latent heat is equal to 27.818 kilowatt. So ventilation load, it is the outside air total heat. So ventilation load is equal to OATH is equal to 49.28 kilowatt. Now we have to calculate grand total heat. So grand total heat, it is the addition of total sensible heat and total latent heat. So total sensible heat, it is equal to outside air sensible heat plus room latent heat, and total latent heat is equal to outside air latent heat plus room latent heat. This room sensible heat and room latent heat, it is given in the numerical, and just now we have calculated outside air sensible heat and outside air latent heat. So by putting these values, we will get total sensible heat is equal to 79.612 kilowatt and total latent heat is equal to 42.358 kilowatt. So we can calculate grand total heat by putting these values. We will get 121.97 kilowatt. Next, we have to calculate grand sensible heat factor. So grand sensible heat factor we can calculate by using formula. Grand sensible heat factor is equal to total sensible heat divided by total sensible heat plus total latent heat. Basically, sensible heat factor, it is the ratio of sensible heat divided by sensible heat plus latent heat. And here we have to calculate grand sensible heat factor. So grand sensible heat factor is equal to total sensible heat divided by total sensible heat plus total latent heat. So by putting these values in this formula, we will get grand sensible heat factor is equal to 0.6527. Now we have to calculate effective room sensible heat factor. So here in this numerical, it is not asked to calculate room sensible heat factor. Suppose if it is asked in the numerical, then we can calculate room sensible heat factor is equal to room sensible heat divided by room sensible heat plus room latent heat. This room sensible heat and room latent heat, it is given in the numerical. So by putting these values, we will get room sensible heat factor is equal to 0.7999. Similarly, we can calculate effective room sensible heat factor. So we can write effective room sensible heat factor is equal to effective room sensible heat divided by effective room sensible heat plus effective room latent heat. Now here we have to calculate effective room sensible heat and effective room latent heat. So we have effective room sensible heat is equal to room sensible heat plus outside air sensible heat into bypass factor. Similarly, effective room latent heat is equal to room latent heat plus outside air latent heat into bypass factor. So by putting these values, we will get effective room sensible heat is equal to 61.3693 kilowatt and effective room latent heat is equal to 18.7127 kilowatt. So by putting these values in this formula, we will get 0.7663. Now we have to calculate apparatus dew point. So to calculate apparatus dew point, we have to draw the process on psychrometry chart. So we have already located point 1 and point 2. Now we have effective room sensible heat factor value, which is 0.7663. So on the sensible heat factor scale, we can locate this point. So here it is 0.75. So here just below that we can locate 0.7663, and here it is the alignment circle. So alignment circle, it is the point on psychrometry chart having value 26 dry bulb temperature and 50% relative humidity. If it is not shown on the psychrometry chart, then we can locate by knowing dry bulb temperature 26 degrees Celsius and relative humidity 50%. Now we have to draw a line connecting these 2 points like this. Then we have to draw a line parallel to this from point 2 like this. So this line, it is effective room sensible heat factor line. So intersection of this line with the saturation curve, it is apparatus dew point temperature. So here this is 10 and for this line it is 11. So apparatus dew point temperature, it is 11 in this case. So effective room sensible heat factor, it is the line connecting room condition and apparatus dew point temperature. So from psychrometry chart, apparatus dew point temperature or TDP, that is dew point temperature, or it is also called as coil dew point temperature, which is 11 degrees Celsius. So in this numerical, we have to calculate up to this only. Now, suppose we have to find out the supply air quantity. That is, after mixing at point 3, how much quantity of air is passing over the cooling coil. So, to calculate that, we have formula effective room sensible heat is equal to 0.02044 into V3. So, V3 it is the quantity of supply air in meter cube per minute into TD2, that is dry bulb temperature at point 2, minus TDP, that is apparatus dew point temperature, into 1 minus bypass factor. So in this formula, all values are known except this V3. So by putting these values, we can find value of V3, that is supply air, which is equal to 252.3035 meter cube per minute. So in this way, we can calculate quantity of supply air. So V1 it is given 70 meter cube per minute, and V3 we have calculated. So we can calculate quantity of recirculated air. So recirculated air VR is equal to supply air minus outside air. So by putting these values, we will get V2, that is recirculated air, 182.3035 meter cube per minute. Now we have to locate point 3 on psychrometry chart. So we can find out the properties at point 3. So for mixing, we can write energy balance. So energy coming along with this outside air plus energy of this recirculated air is equal to energy after mixing. So by writing energy balance, that is M1H1 plus M2H2 is equal to M3H3. This point 2 it is related to recirculated air. Now here this mass flow rate it is volume into density. So density we can cancel on both sides. So we can rewrite this formula as V1H1 plus V2H2 is equal to V3H3. And in this formula, unknown is H3. So we can write H3 is equal to V1H1 plus V2H2 divided by V3. So by putting these values, we will get H3, that is enthalpy of supply air, is equal to 59.7660 kilojoule per kg of dry air. Now we can locate this point on psychrometry chart. So we have point 1, that is outside room condition, and point 2 inside room condition. So here to locate this point 3, which is after mixing point. So if you draw a line connecting point 1 to, then this mixing point will be on this line, because this outside air and inside air will mix. So after mixing, that point will be on this line only. So here we can read the H3 value on this enthalpy scale. So here it is 60. So just before that, it is 59.7660. So from this point, we can draw a line parallel to constant enthalpy lines and extend up to this line 1, 2. So this intersection point, it is point 3, which is supply air point. That is point before cooling coil. And we can read the values respective to this respective to this point. So if you read dry bulb temperature, it is 29, and wet bulb temperature, it is in between 20 and 21, so 20.5. So dry bulb temperature at point 3, it is 29 degrees Celsius, and wet bulb temperature 20.5 degrees Celsius. So from psychrometry chart, after mixing, dry bulb temperature 29 degrees Celsius and wet bulb temperature 20.5 degrees Celsius. Now we will locate point 4 on psychrometry chart. So point 4, it is the point after passing the supply air over the cooling coil. So we have to calculate value for room sensible heat factor, which is equal to room sensible heat divided by room sensible heat plus room latent heat. Room sensible heat and room latent heat, it is given in the numerical, and we have already calculated that value, and we have already calculated that value, which is equal to 0.7999. So we can locate this room sensible heat factor in psychrometry chart. So room sensible heat factor, it is 0.7999. So it is about 0.8. So that point is here. So we can look, we can connect this point with the alignment circle like this, and we have to draw a line parallel to this from point 2 like this. So this line, it is room sensible heat factor line. This previous line which we have drawn, it is effective room sensible heat factor line, and this line, it is room sensible heat factor line. So the intersection of this room sensible heat factor line with saturation curve, it is called room ADP, and intersection of ERSHF line with saturation curve, it is coil ADP. Now we have to look at the point 4. So to look at point 4, we have to draw grand sensible heat factor line. So grand sensible heat factor line, it is the line connecting mixing point with the ADP. So let us connect this point 3 with the ADP. So this line, it is grand sensible heat factor line, and intersection of this grand sensible heat factor line and room sensible heat factor line, it is 0.4, and we can read the values respective to this 0.4. Here it is the 15 degree Celsius dry bulb temperature, and wet bulb temperature, it is here, it is 10, then 11, 12, 13 and 14. So it is in between 13 and 14, so it is 13.5. And we can calculate value of reheat by using enthalpy difference between H2 and H4. So in this way, we can draw effective room sensible heat factor line, which is the line connecting inside room condition and apparatus dew point temperature. Then room sensible heat factor line, it is the line connecting room condition with after coil condition, and if we extend this line up to saturation curve, then this point, it is room ADP. And grand sensible heat factor line, it is the line connecting mixing point and apparatus dew point temperature. So in this way, we can locate different points, like point 1, it is outside condition, point 2, it is inside room condition, point 3, it is after mixing condition, point 4, it is condition of air after passing over the cooling coil, and we can draw different sensible heat factor lines, that is effective room sensible heat factor line, room sensible heat factor line, and grand sensible heat factor line. Thank you.